So we're going to continue now with the separation of variables method. So the first one that we've got here, h, we've got dy dx, and we've got some stuff over here with some y's in it. So what we're going to do is take that to the left side and then take the dx up to the right side. So we're going to have dy over the top of 1 plus 9y squared equals dx. Now what we're going to do, we've done the separation at this point, is just rewrite this so it's a little bit easier to integrate. Integral signs on each side. When we integrate this side, you'll recognise this as inverse tan. So you need to know the formula that a over a squared plus x squared, with respect to x, the integral of that is inverse tan of x on a, plus a constant. So you can see here that it's not in quite the right form. So what we're going to need to do is factor out the 9 first. So get rid of that. So you can see I've just taken the 9 out. 1/9 plus y squared. I can integrate this side because that's just x and a constant. I'm going to take 1/9 out. Now over here we've now got 1/9 underneath. What that means is that we have a third squared, because that's the 1/9, plus y squared. So that means here that we've got a equals a third and y equals x, which I know it seems a bit strange, but essentially the y goes in the place of the x here. So because we also need to have, in this case, the a on the top line of the fraction, we're going to add that in. Now the way we're going to do that is we're going to be a bit shifty and add a third up the top, which is fine. But because we've now multiplied the top line by a third, we are going to divide by a third. Now when you divide by a third, you're essentially doing that, dividing by a third, which we know is the same as multiplying by 3. Dividing by a third is the same as multiplying by 3. So that's why I've popped that 3 out the front. So you can see, simplifying that now, 1/9 times 3 is a third. We can integrate this section here now, which is going to be inverse tan of x over a, which is a third. And we can, of course, simplify that a little bit to 3x. So it looks like that. Now, when we look for y, and because you're often so used to using x, just keep on top of that. Okay, so what we're going to do is we're going to put our conditions in now. So we've got this condition here tells us that when x equals negative pi on 2, y equals negative a third. So we're going to put that in at this point. So we've got x equals negative pi on 12, y equals negative a third. So we're going to sub that in. So we've got a third inverse tan 3 times negative a third, which is negative 1, equals negative pi on 12 plus c. We've got a third. Inverse tan of negative 1 is going to be sitting over here or over here. So because we're looking for inverse tan, just going to the formula sheet, you can see that we've got for inverse tan from negative pi on 2 to pi on 2. So that means from negative pi on 2 to pi on 2 is this section here. So we're going to go with that being the negative pi on 4. And you can see here that we now get negative pi on 12 on the left side, which implies that c is 0. So therefore, we have our particular solution, which is going to be given by a third inverse tan, 3y equals x. Now I'm using that because that is that equation there, now written with c equal to 0. And because you really should be giving this in terms of y, I would rearrange this. So taking the tan over and then dividing by 3. So it ends up being 1/3 tan of 3x. Starting with that, we could differentiate that and we'd end up back in this position here. So the next one that we've got is this one. I'm just going to copy that so I can see it on the next page. So we've got, in this one it's going to be a little bit of work because when we flip this over we're going to end up having to split. So the first thing I'm going to do again, take the y stuff over. I'm going to take that over and I'm going to bring the dx up. I'll actually just leave the 2 where it is because it means I don't have to work with a 2 on this left side where there's a lot more stuff going on. So I can see here that the first identification I have is that this would factor. So I'm actually going to take a 1 out. I'm going to factor that up. And here, just taking the dx and the dy out, integrating both sides. Now this side is easy enough. It's a half x. This side here you'll recognise is a partial fractions question because you have two linear factors there on the denominator. So essentially we're going to just look at that part and do the split. So it equals a on the first factor plus b on the second factor, cross multiply. So you can of course do this, you can do this with Mathematica, or make sure that you can also do it by hand too, because you want to be able to do it both ways. So we're going to look at two values for y here. Y equals -2, which will make this bracket equal to 0, which gives you -2b. So b equals -1/2. And when y equals 0, that will make the b disappear. So you'll get 1 equals 2a. And that tells you that a equals 1/2. So now that we've got that, we can put that back into our integral over here. So instead of writing the integral of, I'll do it in green. Instead of saying, okay, this is the thing I'm going to integrate, we're going to integrate this thing, but with b equals -1/2 and with a equals 1/2 in there. So we're going to be integrating a over y, which is 1/2 over y, minus 1/2 over y plus 2. All of that being equal to 1/2 x. I'm going to take the half out. It's a little bit less hectic, I suppose, than having it up the top there. What you'll recognise at this point is that you can multiply both sides by 2, and in doing that we actually get rid of the fraction altogether. We do though introduce a 2c, so feel free to relabel that. On the next line we're going to do that. These two things turn into logs. I'm going to call this k, where I've let 2c equal k. I'm just relabeling an arbitrary constant. I've got a subtraction here of logs, so I can do one over the other. And that's it at that point. Now we're going to put our condition in. So the condition is going to be y equals -4, x equals 0. It's going to be nice actually, because in this case you can see that straight away you end up with this being equal to k, because x is 0. In the bracket here you've got -4 over -4 plus 2, which is -2. So that is 2. And this implies then that k is log 2. You don't need the modular signs around that because it's positive. So to finish off, we've got log of y over y plus 2 equals x plus log 2. Now with that you might like to go a step further, and in doing so you might like to simplify it a little bit using exponentials. I'm just going to pop that on this page. So what we could do is we could take exponentials of each side. And here you've got your exponentials, which will cancel out. Here you've got e to the x times e to the log 2. It's multiplied because you have an addition here in the exponent. Here you've got still that fraction, e to the x. You can relabel this because this is, not relabel it, you can eliminate the e in the log. So this is actually just 2. And bring the y plus 2 up. And this is actually going to allow us to get y on its own, because we're going to have this situation where we can bring all the y stuff to the left side, factor out what's common. Oops, I did that weirdly backwards. And then your solution to finish off would be y equals 4e to the x over 1 minus 2 e to the x. So after all that work, what originally was a log back here, and actually started off with all sorts of just powers of y, ends up being all exponentials, which is pretty neat. So the last one that we're going to look at here is these two. These ones are actually pretty little. So this is looking for the family of curves. So this will be with the plus c. So Again, we're going to do the split here. These ones are pretty quick, so oops, I'm going to bring the y squared up, integrate both sides. We're going to have y cubed on 3 equals x plus c. Y cubed equals 3x plus 3c, and hence y equals the cube root of 3x plus k. I've just said that k is equal to 3c, so it's simplified a little bit. So that is A. And B, similar idea, writing it out, swapping over the y stuff and the x stuff up. So we're going to have dy over 2y take 1. I'm going to just rewrite that slightly, so it's easy for me to put the integral signs in. This is going to be a half log of 2y minus 1. The reason for that is that the rule is when you're integrating a linear factor like that, it's going to be the log, 1 over a, or you can think of it, if it helps, as being the log of the thing underneath divided by a plus c. Yep, and on this side we're going to have x plus c. Again, a bit of like manipulation. You can see here that the 2 would come up and be a 2c, so I'm just going to call that k. And here we can take an exponential of each side, rise it up like that. 2y equals e to the 2x times e to the k plus 1. And we know from previous work, I'll just move this all up a little bit. Oops. Let's move it over there. We know that those two things there, or in particular this thing, can be relabeled as a constant. So the solution for this one is going to end up being, oops, I'll just copy that over. Just getting it in terms of y. I nearly got it all on one page. It's very sad. Oh, it's not coming over. Come over here. Boom. Okay, so this can be rewritten. So we'll rewrite it as 2y equals a e to the 2x plus 1. What we've done is let e to the k equal a. And then finally y equals a e to the 2x plus 1 all over 2. So that would be our solution. So that one has a few steps in it, just because you're rearranging your logs and then relabeling constants. What you can do is, if you want to, don't relabel the constants all the way through, just work with it as C, and then at the very end you can relabel it so you don't have as many changes all the way through. But that's the idea of separation of variables.